Next we have pure capacitive process. So here we will draw the Bode diagram. Bode diagram for your capacitive process. Capacitive process. So for pure capacitive process, the transfer function is the transfer function G of S equal to dP upon S. So substitute S equal to J omega. We will find amplitude ratio as the modulus of J omega. So this will be equal to Kb upon J omega. So the mod of, so this can be written as the mod of Kp, the complex conjugate of J omega, that is minus J omega, and the mod of J omega square. This will be omega square. So finally we will have the mod of minus Kp J omega. So here we have omega get cancelled. So we will have minus J Kp upon omega. So this will be equal to under root of real part of this complex number. This will be 0 square plus minus Kp upon omega whole square. So the amplitude will be equal to Kp upon omega. This will be the amplitude ratio. So this is equation number 2. So now taking log 10 of AR will be equal to log 10 of Kp minus log 10 of omega. So here log 10 of longitude ratio by Cp will be equal to minus log 10 of omega. So at log scale, so this will be the equation of line. So this is the equation of line. So this is y equal to and x on log scale. So the slope will be equal to minus 1. So next, coming to phase. So the phase phi can be given as the argument of j of j omega, and that will be equal to the argument of j minus kp upon omega. So this will be equal to 10 inverse the imaginary part to the real part. So the imaginary part will be 10 inverse imaginary part is minus kp upon omega, and the real part is 0. So we will have minus 10 inverse minus infinity. This will be equal to minus 90 degree. So phi will be equal to minus 90 degree for phase shift in this equation number 3. This is equation number 4. This will be. Now we can plot the Bode diagram, and y axis this will be x axis will be omega pp, and y axis will be e, and let's say here we have 1, this is 0.1 and 0.01. Here we have 0.01, and here we have 0.1. This is 1, and this is 10. So from this expression, ES upon Kp is equal to omega inverse. So it means E r upon Kp equal to omega inverse. So this is 1 upon omega, right? So when omega is equal to 1, so this ER upon kp will be equal to 1. So when omega equal to 1, so this ER by kp equal to 1. So for 1 unit here down, this should be pass through. Okay. So finally the expression for gain plot. So finally gain plot will be like this. So here the slope will be -1. Similarly, the phase plot will be equal to, this will be omega, and here we will have phi, and so this is again 0.01, this is 0.1, this is 1, this is 10. So at omega equal to 1, so at omega equal to 1, so from the phase expression, so phi will be equal to 90 degree for all value of omega. So here for all value of omega, the phi will be equal to -90 degree. So this will be the phase plot. Similarly, we can, so this is the gain and phase plot of transportation light system. This is the gain and phase plot of pure capacitive system. So next, let's discuss the Bode diagram of next so the next let's discuss the Bode diagram of transportation system transportation system. So the transfer function for transportation lag system is the transfer function for transportation lag system is g of s is equal to exponential minus e to the power minus tau ds. So tau d is this is equation number 1. So where tau d is the delay time of the system delay time of the system. So now let's find the amplitude ratio. So amplitude ratio will be the magnitude of g of j omega, and this will be the magnitude of e to the power minus tau d j omega, and this can be written as modulus of e to the power minus j omega tau omega tau d. So the mod of exponential is 1. So the amplitude ratio is 1 for all omega. So the phase can be given as the argument of capital G of j omega, and that will be equal to the argument of e to the power minus j omega tau d, and this will be equal to e to the power j minus omega tau d. And therefore phi will be equal to minus omega tau d in radian. So this will be the equation number 3. So when omega tau d is 1, so when omega tau d is 1, the phi will be equal to minus 1 radian, and that will be equal to minus minus 57.29 degree. This will be question number 4. So now we can draw the phase plot as well as gain plot for this system. So for gain plot we will have omega on the x-axis, and here we will have amplitude ratio, and let's say this is 1 equal to omega tau d. So we are just plotting AR versus omega tau d. So when omega tau d is equal to 1, so when omega tau d is 1, so the amplitude ratio is also 1. So as amplitude ratio is constant for all omega, so this will be the amplitude ratio plot for transportation lag system, and this is, let's say, 0.01, and this is 100. This is 0.01. So for phase plot we can again, let's say this is omega tau d, so we are just plotting phi against omega tau d. So at when omega tau d is 1, so when omega tau d is 1, so the angle is minus 57 degree. So the angle is minus 57. So when omega is 0, so the angle will be, when omega is 0, so when omega is 0, omega tau d tends to 0. It means phi will tends to 0. So this will be 0 degree. So when omega equal to 1 upon tau d, it means omega tau d equal to 1. In that case phi will be equal to minus 57.29 degree. So at this point, this is 57, this is 0. So when omega tau d equal to, let's say, 10, in that case phi will be -57, that will minus 570.29 degree. Sorry. So in that case, this will be 572.9 degree. So when omega tau is 10, so we will have 10 here, we will have 100 here. So at 10 we will have 572 degree. So here we will have minus 57.29 degree, and here we will have minus 572.9 degree, and this will be at 10. So finally we will have the phase diagram like this. So this is the phase diagram for transportation lag system. Now coming to section, that is Bode plot of controllers. So let's say first P controller. So for P controller, the transfer function is Kc. So therefore amplitude ratio will be Kc e to the power j 0 so the amplitude ratio will be Kc for all omega, and phi will be equal to argument of this Kc e to the power j 0, and that will be equal to 0 degree for all omega. So therefore the phase plot and gain plot will be like this. So we will have omega here and amplitude ratio will be here. So AR by KC. So if we take the log AR both side, so this way this can be written as log 10 AR by KC equal to log 10 that is 0, and therefore this will be AR by K will be equal to 1. So in this case we will be having 1 here, and let's say 0.01 here, 0.01 here, this is 1 and this is 100. So for gain plot for all omega, AR by KC will be equal to 1. So this will be the gain plot for peak controller. Similarly, the phase plot can also be plotted this way. This is omega and this is 5, 7 omega, and this will also 0 for all omega. So we will have the gain plot like this. So the phase plot will be like 5 will be equal to 0 degree for all omega. So this is Bode plot of P controller. So this is the Bode plot of P controller. So the next in the next for section B, we have, let's say, PI controller. So for PI controller, the transfer function G of S will be equal to KC 1 plus 1 upon tau I S. This will be the first equation. And this is, let's say, equation number 5. So the amplitude ratio So the amplitude ratio will be equal to the mod of g of j omega. So substitute, so this will be like kc 1 plus 1 upon j omega tau I. So further simplifying, we will be having the mod of kc 1 plus, and this can be written as 1 upon z, where z is j omega tau I. So z inverse, and this z inverse can be written as the, so using this property, z inverse can be written as the complex conjugate of z upon the mod of z square. So using this property, this 1 upon z can be written as 1 upon j omega tau, can be written as j omega tau I inverse. So the complex conjugate of j omega tau I, the complex conjugate of this can be written this, and this will be omega tau I whole square, and this will be finally the mod of kc 1, and this can be written minus j upon omega tau I. So here the amplitude will be kc under root 1 real part square plus imaginary part square, and that will be equal to kc under root 1 plus 1 upon omega square tau I square, omega square tau I square. So this will be the amplitude ratio. So the amplitude ratio is, this can be written as amplitude ratio upon kc equal to the root 1 plus 1 upon omega tau I whole square. So this is question number 6. So further taking log 10 AR by KC will be equal to minus half, so will be equal to plus half log tan 1 plus 1 upon omega tau I whole square, and this will be the equation number 7. So for phase shift phi can be written as tan inverse the imaginary part of g of j omega, the real part, and that will be equal to tan inverse, and the imaginary part is minus 1 upon omega tau I. So the imaginary part is 1 upon omega tau I, and the real part is 1. So the phase shift is tan inverse minus 1 upon omega tau I. So this is equation number 8. So finally we can plot the gain and phase plot against the frequency. So here let's say we have 3 region. So when omega tends to 0, so the amplitude upon PDC, and here we have phi. So using equation 7 or 8, when omega tends to 0, so when omega tends to 0, so 1 upon omega square tends to infinity. So we can take 1 upon omega square tau I square common. So here we can see when omega tends to 0, it means 1 upon omega square tends to infinity. So in that case, using this expression, equation number 7, So this can be written as half. So we can take this outside. So finally we will get log of 10, and then we will have 1 upon omega tau I whole square, and here we will have omega tau I square plus 1. So when this omega is 0, so we will have minus log so 1 upon omega square will be infinity, right? This will be log 10 1 upon omega tau I whole square. So we will get log 10 1 upon omega tau I. So in that case, this when omega tends to infinity, when omega tends to 0, so this AR by KC tends to 1 upon omega tau. So this will be 1 upon omega tau I. Similarly, when omega tau I equal to 1, so at the corner frequency, we will have omega tau I equal to 1. So in that case, log 10 AR by KC will be equal to half log 10 1 plus 1 upon omega tau I whole square. So this will be 1 plus 1 upon 1 whole square. So this will be log 1 plus 1. So this will be log 2. So this is log 10 of 2 under root. So it means AR by KC equal to root 2. So when omega tau I equal to 1, means when omega equal to corner frequency, in that case AR by KC will be equal to 0.707. Sorry, this is wrong. So when omega tau is equal to 1, so this will be equal to root 2, and this will be equal to 1.4 1. So also when omega tends to infinity, so this log 10 AR by Kc will be equal to log half log 10 1 plus 1 upon omega tau whole omega tau I. So omega tau I whole square. So when omega tau I square equal to infinity, so in that case in this case 1 upon omega square tends to 0. So it means log 10 1. So it means AR upon Kc tends to 1 when omega tends to infinity. So therefore when omega tends to infinity, so this will be AR by Kc tends to 1. Similarly we can find the phi for these three regions. So for these three regions when omega tends to 0, so when omega tends to 0, so phi will be phi 0 will be tan inverse, so this will be tan inverse minus infinity, and that will be equal to minus 90 degree. Minus 90 degree. When omega tau is equal to 1, so this will be tan inverse minus 1, and this will be equal to minus 45 degree. So when omega tends to infinity, this will be tan inverse minus 0, and this will be 0 degree. So using this information we can now plot the gain plot for gain plot for PI controller. So this is, let's say, omega tau I, we will not plot the gain plot as AR by Kc versus omega tau I. So instead that we will plot amplitude ratio upon Kc versus omega. So when omega tau equal to 1, when omega equal to corner frequency, so it means the corner frequency will be 1 upon tau I, and this will be your corner frequency. So this will be your corner frequency. So at corner frequency, the value of AR by Kc will be 1.41. So the value of AR by Kc will be 1.41, and for omega, when omega tends to 0, so AR by Kc will be equal to 1 upon omega tau I, and when omega tends to infinity, AR by Kc will be equal to 1, right? So we will just extend this line, vertical line. So extend 1 upon omega, 1 upon tau I along the vertical axis, and in y-axis, let's say this is 1 and this is 0.01, this is 0.01, and this is somewhere, let's say 1, and this is 100. And when omega is greater than corner frequency, so just draw a horizontal line which is passing through AR by Kc equal to 1. So when omega is greater than corner frequency, we have AR by Kc approaches to 1. So for omega tends to infinity, so this AR by Kc approaches to 1. When omega is equal to omega c, means 1 upon tau I, so the value of (1.41). So now we can plot the gain plot like this. So PI controller, the gain plot will look like this, and the phase plot can also be drawn similar way. So this is, let's say, phi in the y-axis, and this is omega, and this is again 100, this is 0.01, and this is let's say 1, and let's extend this corner frequency along the vertical axis. So this is 1 upon tau I. So when omega tau is equal to 1, the phase is minus 45, right? So when omega tau is equal to 1, so here we have 3. So this is 90 degree, this is minus 45 degree, and this is 0 degree. So when omega is equal to corner frequency, that is 1 upon tau I, the angle is 45 degree. When omega is equal to 0, so the angle is 90 degree. When omega is equal to infinity, so then the angle is 0. So the phase plot can be drawn like this. So we will start from minus 90 degree when omega is equal to 0, and then up to 0. So this is the phase plot for PI controller. So this is the Bode plot of PI controller. So for section C, for PD controller, the transfer function will be GS can be written as KC 1 plus omega 1 plus tau d s. So this is equation number 9. So this is, let's say, equation number 9. So the amplitude ratio can be written as the mod of G of J omega and this can be written as Kc 1 plus j omega tau d, and further this can be written as Kc square root of the real part of complex number. So this will be 1 square plus omega tau d whole square. So the amplitude ratio will be equal to under root AR by Kc equal to 1 plus omega tau d whole square. So this is equation number 10. So taking the log 10 both sides, we will be having log 10 AR by Kc equal to half log 10 1 plus omega square tau d square, and this is equation number 10.1. The phase shift phi can be written as tan inverse the imaginary part of g of j omega upon real part of g of j omega, and which further can be simplified as, so this will be Kc omega tau d, this is the imaginary part upon real part, that is Kc. So Kc cancel out, so we will be having phase shift as tan inverse omega tau d. This is equation number 11. So again here we will have three regions. So we will find out AR by Kc in each region and the corresponding phi value for each region. So let's say when omega tends to 0, so in that case AR by Kc will be equal to in that case AR by Kc equal to, so using equation number 10.1, so log 10 AR by Kc will be equal to half log 10 1 plus 0. So this will be, so it means AR by Kc will approach to 1 and phi will approach to tan inverse 0. So phi 0 will be equal to tan inverse 0, and that will be equal to 0 degree. So when omega tends to infinity, so in that case log 10 AR by KC equal to half log 10 1 plus infinity. So if we take omega square tau d square common, so we will get half log 10 omega square tau d square 1 upon omega square tau d square plus 1. So first term will tends to 0, so we will be having omega square tau d square, and that will be equal to, so in this case the expression will be half log 10 omega square tau d square. So it means omega tau d whole square. So 2 we will take 2 out, and so we will get log 10 omega tau d. So finally here we will get AR by KC will be equal to omega tau d, and phi at infinity will be equal to 10 inverse omega tau d. So 10 inverse omega tau d will be equal to so when omega tends to infinity, so phi infinity will be 10 inverse infinity, and that will be equal to plus 90 degree. So when omega tau d equal to 1 and or omega c equal to 1 upon tau d. So in that case log 10 AR by KC will be equal to 1 by 2 log 10 1 plus 1, and that will be half log 10 2, and which can be further simplified as log 10 under root 2. So AR by KC will be equal to under root 2, that will be equal to 1.41, and phi at this point at the corner frequency can be written as 10 inverse 1. So this will be 45 degree. So using this information we can draw the Bode diagram for PD controller. So now let's draw the Bode diagram for PD controller. So first we will draw the gain plot. So x-axis is omega and y-axis is y-axis is ER by KC. And let's say this is 1 upon tau d, which is a corner frequency. So the corner frequency is 1 upon tau d. So first we have to locate the 1 upon tau d on the omega axis. So when omega tau d is equal to 1, the amplitude ratio is under root 2, 1.41, and when omega tends to 0, we have ER by KC is equal to 1. So ER by KC equal to 1, when omega is less than corner frequency. So now let's draw a vertical line which pass through this corner frequency omega equal to omega c. So at this corner frequency, the value of gain is 1.41. So the value of gain is 1.41, and this is, let's say, this point. So this is the gain at the corner frequency. So when omega tends to 0, ER by KC tends to 1, and when omega tends to infinity, so the gain equal to omega, ER by KC is equal to omega tau d. So in this case, this is omega tau d is equal to 1 line, and this way we can plot the gain this way. So when omega equal to 0, so the gain will be 0, and this will further increase and approach to this line. Phi 0 tends to tan inverse 0, that is 0. So this is 0 degree, and this is phi axis when omega tends to infinity. So this is phi equal to 0 axis, and this is phi equal to plus 90 degree axis. And when omega tau d is equal to 1, means omega is equal to omega c, that is 1 upon tau d. So at this point when omega is equal to omega c, and this is equal to 1 upon tau d. So in that case the angle is 45, phase shift is 45 when omega tends to 0. So this tan inverse 0 equal to 0, so the angle is 0. When omega tends to infinity, so the phase shift will be tan inverse infinity. So the overall phase plot can be drawn like this. So this is the Bode plot of PD controller. And so the last section is PID controller. So the transfer function for PID controller, G of S, can be written as Kc 1 plus 1 upon tau I s plus tau d s, and this is equation number 12. So this is equation number 12. So the G of j omega can be calculated as 1 plus 1 upon j omega tau I plus j omega tau d, and which further can be simplified as 1 plus minus j omega tau I upon omega tau I whole square plus j omega tau d So we will have Kc in bracket 1 plus J in bracket omega tau d minus 1 upon omega tau I. So the real part is of G of J omega. So let's say this is the real part R, which is Kc, and the imaginary part I is the imaginary part of G of J omega, and this will be equal to Kc omega tau d minus 1 upon omega tau R. So the amplitude ratio is the mod of G of J omega, and that will be the square root of real part square plus imaginary part square, and here we can put the Kc square plus Kc square and omega tau d minus 1 upon omega tau I whole square and square root, and further we can write here equal to Kc under root 1 plus omega tau d minus 1 upon omega tau I whole square. So this is the amplitude ratio for the PID controller, and this is equation number 13. The phase shift can be written as tan inverse imaginary part upon real part, and that will be equal to tan inverse omega tau d minus 1 upon omega tau R. So this is the imaginary part and this is the real part. So now Kc will cancel out, and we will have the expression for phase shift, that is tan inverse omega tau d minus 1 upon omega tau R, and this is equation number 14. So here again we will So taking log 10 of equation 13. So taking log of equation 13, we will have log 10 AR by KC equal to half log 10 1 plus omega tau d minus 1 upon omega tau I. Whole square. So this is equation 13.1. So here we will have again different regions, and we will find out AR by KC and phi for those regions. So when omega tends to 0, means this omega tends to 0 and this will tends to so this will 0, this is minus omega tau I, so omega tends to 0, this is 0, so minus infinity, so 1 plus omega square tau I square, taking common, so minus plus 1 upon, so here we will have, so AR by KC will be close to 1 upon omega tau I, and phi 0 will be equal to, so phi 0 will be equal to tan inverse 0 minus infinity, so 0 minus infinity, so this will be minus 90 degree. So when omega tau d equal to 1. So at the corner frequency, when omega equal to 1 upon tau d, so AR by KC will be equal to 2 and the phi at 1 upon tau d will be equal to 1 will be equal to, so when omega tau d is equal to 1, so this is 1, right? So this will be omega is equal to 1 upon tau d, so this will be 1, so it will be something more than 40 plus, so this will be much lesser than 45 degree. So when omega tau I equal to 1, the another corner frequency, this will be under root 2 and phi 1 upon tau I will be equal to greater than 45. So when omega tau is equal to 1, so in this case, let's say we are assuming that this tau d is much higher than, so we are just assuming that we are assuming tau d is much greater than tau I. So in that case, 1 upon tau d, so in that case 1 upon tau d will be less than 1 upon tau 45 degree, and when omega tends to infinity, so this will be infinity and this will be 0, so you can take this out here. This will be 1. So when omega tends to infinity, hereby this will be equal to half log band 1 plus omega tau d. And phi infinity, so phi infinity is 0. So then mass infinity, that is plus 90 degree. So So now we can plot the gain plot. So here we will have AR by KC, and this will be y-axis, and this will be omega axis. So here we will have omega axis, here we will have phi axis. So let's say we have tau d is much greater than tau, so 1 upon tau d will be less than, so this is, let's say, 1 upon tau d, and this is 1 upon tau I. So let's say this is 1, this is 10, and this is 0.1, and here this is 1, this is 0.1, and this is 10. So when omega tends to 0, so AR by KC is equal to 1 upon omega tau I. So in this case we will have a line which will have a slope of -1. So this will be the one upon omega I tau I, and this will be the 1 upon omega d tau d, and at this point, so this way so this is the gain plot, and for phase plot, for the phase plot the maximum is plus 90 degree, and this is, let's say, minus 90 degree, and this is plus 90 degree, and here we have 0 degree, here we have 45 degree. So for phi 1 upon tau d, phi 0 90, so at 0 the angle is 90, and when omega is equal to 1 upon tau d, so this will be minus 45 degree S. So this will be minus 45. So this is 0, 45. This will be somewhere here. And when omega equal to omega c I, in that case, so this will be plus 45 degree. So this will be 45. So here we have and again we continuously this is and this is minus and when omega tends to infinity, so when omega tends to 0, we have phi equal to minus 90, when omega equal to 1 upon tau d, so we have minus 45 degree less. When omega is greater than 1 upon tau I, we will have plus minus, so this will be plus. So this is the Bode diagram for PID controller. Thanks for watching. So that's all for today. Thank you.